Hi and welcome. Today I want to talk you through some very cheap but very effective and very versatile resources, being counters, cards and cubes. The things that I explain about the counters can also be done with the cubes. These though come into their own when we start talking about volume, and I'll unpack that a little bit later. The easiest and most obvious thing to do with the counters is to practice counting. 1, 2, 3, 4, 5. And this is also helping them with their one-to-one correspondence. One-to-one correspondence is so that they can match a number with a counter. So instead of saying 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, they're actually going 1, 2, 3, 4, 5. The next thing I want to talk about is something called subitizing or subitizing, which is instantly recognizing a number of dots. So in this example, we can see that the number 4 has been represented in multiple ways. Now, a good way to do this with your child is to put them out, ask them what they see. So I see 4, but then also ask them how they see it. They may see it as 2 rows of 2. They may see it as 2 columns of 2. They may just say, I see 1, 2, 3, 4, and that's okay as well. It depends on where they're up to in their development. But you can do this for any number, probably no more than 6 to start with. But as they get older, they start to chunk numbers together with these patterns so that they can see bigger numbers. So for example, if we're looking at just this section, they'd be able to see, I see 8 because I can see 4 and 4. Or they might say, I can see 8 because I can see 3 and 1, which makes 4, and 2 and 2, which makes 4. Something that you can do is just scatter some counters, flatten them all out perhaps, and then ask your older child how many they see in total. So they might see 3, 3, 4, and 3. They may then say that they know that that is 7 and 3 more is 10, so the total is 13. Counters are great for creating and describing patterns. So if you were to create this top pattern, you could ask your child to describe what they see. They may say to you, I can see red, blue, red, blue, red, blue. They might say they could see red and blue, and then that keeps getting repeated, which is great. You could also ask them, okay, well, what color comes next? And they'll say red, which is right. But rather than leaving it there, how do you know? How did you know? How did you work that out? All these questions help them think out loud and use their mathematical terminology. The second example is just a slightly different pattern. But again, it would be, okay, well, then what comes next? And the child might say, okay, I'm not sure. So then you can walk them back through the pattern. They might say, well, it has to be yellow because every orange is followed by a yellow. What would come next? Then they would do the same thing. So patterns are an easy way to use these counters. For our very little people, we can also use the counters to help them understand the idea of the friends of 10 or bonds to 10. So we can see that 5 and 1 make 6. 5 and 2 make 7, make 8, and so on. And they can actually see that 5 and 5 make 10. With the number bonds to 10, or the friends of 10, we can also look at it and look at early combining and separating strategies, because we can see here we've got 8. So we know that 8 and 2 more make 10. But we can also see that in the reverse or the inverse operation, which is 10, when we take 2 away, we end up with 8. Very early on, the children will be introduced to even and odd numbers. Even numbers can be displayed in 2 equal rows, whereas odd numbers can't. And children often have difficulty in understanding the difference between an even number and an odd number. So seeing it represented like this, and again, it's a great use of the counters, can really establish that thought in their head and that idea in their head that we can put an even number into 2 even rows, but odd numbers we cannot. In the early years, the numbers 11 to 20 can be quite challenging because of the way we say the word, but the way the number is actually structured. So 10 and 1 more is 11, whereas if it was 20 and 1 more, it would be 21. So these teen numbers can create real difficulties, but looking at them in this way and using the counters, we can see that 11 is made up of 10 and 1 more. 12 is 10 and 2 more. 13 is 12 and 3 more. And we can see by this structure that we have an odd number because we cannot put 13 into 2 even rows. Combining and separating are the words that we use when we talk about addition and subtraction in early stage 1 and stage 1, so from kindergarten right through to year 2. The words addition and subtraction start to sneak in stage 1, but we can use the counters to demonstrate these things. So we have 4 and 2 more. What do we have? We have 6. We have 3 more. What do we have? We have 9. If we have 9 and we separate some or we take some away, and let's say we take away 3, what do we have? We can see that we have 6 left. But what we can also see is that we have one part and another part, and when we put the parts together, we make the whole. And so this part-whole relationship starts to be taught in stage 1 so that we can see those links later on. In the early years, we talk about forming groups. So here we can say we have 2 groups of 3, or we have 3 groups of 2. Either way, we have 6. When we have 6, we can also share those into 2 groups, which we have 3 each. So that's the beginning of division. Or we could share them into 3 groups, which is 2 each. So you can see that we can link multiplication and division, and we can demonstrate it using the counters. The other thing that we can do when the children are ready for it later in their learning is to describe square numbers. So square numbers are square numbers because they form a square. 3 rows of 3, 3 columns of 3, it doesn't really matter. It forms a square, and we have 9, we know is a square number. We can demonstrate doubling and halving. So here we have 2. If we double 2, we have 4. If we halve that, doesn't matter how we do it, we end up with 2 again. Another great way to use the counters is, particularly in the younger years, is to use it as an informal unit of measure. So they don't start using centimetres, metres and millimetres till much later on. So in this example, I've got the pen, and we can see that that is 2, 4, 6, 8, 9 counters long. The paper clip's only 2 and the pen is only 1. So you could have your child go around the house and find something that is about 10 counters long. So if we know the pen is 9, they could take that around and measure that against some of the other items in their house to find one that's 10 counters long. Using counters or the cubes for arrays to show, to demonstrate, and therefore explain multiplication and division are one of the best ways to use these. Here we can see we have 4 rows of 3. We have 3 columns of 4. We have 12 in total. If we share those into 4 groups, we have 3 in each group. If we share them into 3 groups, we have 4 in each group. We call those fact families, and those fact families are practiced over and over at school, but your help at home would be so helpful as well, because these are the sorts of things that they need to be able to see, to understand, and also then be able to tell you all of the facts that they can see out of that. They might also then just say, like, if we change it slightly, we have 12 in total again. So we're looking then at factors, and we have 2 rows of 6 or 6 groups of 2. We have 12 again, but if we split it into 2 groups, we have 6 in each. If we split it into 6 groups, we have 2 in each. Using the counters as an informal unit of measure to measure the area of something is also a great way to use the counters. Now, this might be a little tedious for some of you little people. So if we can see that this Post-it note has an area of 16 counters. Now, they may be able to have to count each one of them individually. They may be able to say 4 and 4 is 8, and 4 more is 12, and 4 more is 16, or they may count it a different way. But then you could have them go around the house with the Post-it notes, not the counters, and find things that have the same area as that. I've put this data collection, or this graph, that terminology doesn't get used till later on, but I've put this data collection together. But you could just scatter some counters and have your child put them together in colour organisation, and then ask them, what do you see? What do you notice? What do you wonder? These questions are great at making your child look further than just the pretty colours. So they may say something like, well, blue has the most, and that orange and red have the same amount of counters, and that purple and green have the same amount. Okay, how many counters altogether? Now they might have to literally count each one, or they can use their maths, use their addition skills, use their facts, and they could add that up to see how many counters they have in total. These graphs, these data displays are also useful when they're learning later in stage 2 and 3 that 1 represents more than 1. So this might represent 10. So then those same questions can be asked, but we understand that each one of those represents 10 or 2 or 450 or whatever the case may be. But they're great for showing the representation of the data, and then from there they can interpret that data. We can also use the counters to describe chance events. In this case, if these were in a bag, we would be more likely to pick green than red. In this example, it would be impossible to pick any other colour but blue. And in this example, we can talk about the chances of being equally likely to pick yellow or orange. The terminology equally likely is not introduced until stage 3. Using the ace as a 1 is okay, but sometimes using the 10 cards can be a bit problematic because it affects our place value. So for some of these activities, you might want to take the 10 card out. And so now we have 13 or 313 or 3,135. Cards are a great resource for just numeral identification. So 4, 7, 8, 3. Keep going. You could even make larger numbers, 47, 83, hundreds, thousands. Then, and interestingly, I'll just show you this while I've got it, that you can make bigger numbers. Once you start to get into the tens and hundreds of thousands, we used to use a comma here, but we don't use that anymore. So we just use a space. So this would be read as 478,353. We can play the old game of snap, and when we get to snap, so 4, we need to add them. So that's helping another way just to adding into a game that we have been playing with our children for a long time. You could deal out a random set of cards. Let's just use 3 for this example and decide beforehand whether you're going to make the largest number possible or the smallest number possible. So we turn our cards over, manipulate the cards to make the largest number in this case, and then compare it with, let's put 3 more out to say that they are yours. So these are my cards. These become your cards. The largest number you could make, is 872. So in that case, my number is larger than your number. You could talk about how much larger mine is, so the difference between the two numbers, or you could then just put those to one side for a moment. You could then talk about, okay, if that's the largest number, then what's the smallest number? And we can use the same cards to rearrange the number to make the smallest number. Let's go back to the largest number. And then you can talk about, let's make the second largest number. Now, usually the kids swap these two around, but that's not obviously the second largest number. The second largest number is still going to be in the 900s, and this is 74. We need to swap these two around. We still have 947 would be the second largest number. If we were going to do the second smallest number, that's the smallest number that stays in the 400s. Now this is the second smallest number. As a random generator for tables or multiplication facts, 8 sevens, 56. 6 sixes, 36. 2 sevens, 14. 5 nines, 45. If we stop there and we go, okay, well, what else does that tell us? We've got 5 nines, we've got 9 fives. We know that 45 divided by 9 is 5, and we know that 45 divided by 5 is 9. There are the fact families that I talked about earlier in the video. With the multiplication facts, you can also just play a game where it's the winner gets the card, so the highest number, or the lowest total, depending on what you choose, gets the cards, and then you play until all the cards are gone. So let's have a go. So we've got 7 8s are 56, and then 2 4s are 8, so 56 would take those cards. They go back in the pile. Next ones. 7 9s are 63, and 7 5s are 35. So I'd take those cards, those go back. 2 6s are 12, 6 4s are 24. You take those cards, I put them back. And the game continues until all the cards are gone. We can just use them to create random numbers that we can then add. So let's take 78 and 49 and use one of the strategies that they're working with at school to solve that problem. If you wanted to use the cards as a random number generator to do subtraction, this is going to be problematic. We know that we can do negative numbers, but the children don't get taught this until stage 3. So you might want to talk about the fact that we take away the smaller number from the bigger number, and then with a mental strategy, we could do 87 take away 66. Another thing we can use these for is for manipulating area. So if this has an area of 12 blocks, we can keep the 12 blocks, but we can change it so that now it was 4 rows of 3, or 4 rows of 3, or 3 rows of 4. We could make it 2 rows of 6, or 6 groups of 2. Again, this is those tables and those multiplication factors. It all wraps in and it works really well with area. We could make it into a compound shape, which looks like this. And it still has an area of 12 blocks, but you can see that the shape of the area that it covers changes each time. So your child could investigate the different ways that area can be represented by the same number of blocks. We can use these to help your child understand how to work out the area of a compound shape. So this again is very simple, but if we looked at it, we can work out the area of this part, we can work out the area of this part, and then we put the 2 parts together. That's one way. We could do it this way, 1 section, 2 sections, but in this example, because of the way I've built it, that would be the most obvious way to solve that problem. One of the other great things you can do with these blocks is to build a 3-dimensional model and then look at it from all the different aspects. So at school, they might do something like this, and they would be asked to draw the front view, the side view, and then the top view. Something they might also be asked to do is to create those views, a drawn view, and then swap it with a partner, and from the drawings to create the 3-dimensional object. Now, initially, we might think that that's a solid object, but as we turn it, as we manipulate the 3 dimensions of this design, we can see that it's not solid. So this is a really good way for your child to look at the different aspects of the object that they've been given, and then be able to problem solve to work it out so that it can look like those drawings, but in a 3-dimensional way. One of the greatest ways to use these linking cubes is by looking at and deconstructing our understanding of volume. Now, volume is the amount of space that something takes up. And in the very early days, we don't talk about formulas, we don't talk about centimetre cubes or metre cubes, we don't talk about any of that. They will pack blocks into boxes and they will see how many blocks they can fit in. But let me show you. So we can see this has a volume of 6 blocks. We can see that it is just all in one layer, but that layer consists of 2 rows of 3 or 3 rows of 2, depending on how you're looking at it. When we add another layer on top, we can now see that we have 2 layers. And even though these aren't connected, you would build it better than I have. The children can now see that there are 2 layers exactly the same. There is 3 at the bottom. There are 2 rows of 3 at the bottom, and there's 2 layers. So you can already see that we have got the 3 by 2 by 2 formula happening, but we're not introducing that at all at this stage. Then if we could connect another layer, we can see that the layer is still exactly the same. We have, each layer has 3 rows of 2 or 2 rows of 3, and now it is 3 rows high. And then the last, let's look at the last one, that silly blue one. We now have 4. Now, they could go 6, 12, 18, 24. They might see that straight away as 4 groups of 6, again, 24 blocks. If they were to build this at home, you could ask them questions like, how many blocks are in each row? Of course, there are 6 blocks in each row. How are they made up? There's 3 rows of 2 or 2 rows of 3. And how many layers do you have? I've got 4 layers. I've got 4 groups of 6 blocks. So they start to get the picture of what this looks like in their head. When they are 100% ready and nowhere near before this, they'll come up with their own way to describe how to calculate the volume of that block. They won't do it straight away as the formula that we all know. They will do it in their own terms, and then, and only then, does the formula get introduced to them, and then they have this real aha moment that, but of course, it's the length by the width by the height. But introducing it before they're ready is going to come all of this crashing down.